Hello, am I audible? Am I audible now? Okay, and the screen is visible, right? Okay, then we'll begin. So, hello and welcome to the second week of the NPTEL problem solving session for the course Advanced Power Electronics and Control, which is taught by Professor Avik Bhattacharya. So, my name is Saleh Khan, and I'm a PhD student at IIT Delhi, and I'll be conducting these problem solving sessions on Monday from 6 to 8 p.m. So again, just like last week, we'll today begin with a brief summary of the course content that was taught, and then we'll move on to some sample problems. So this week, since the deadline for the assignment submission is 9th, and since you still haven't passed that deadline, so we'll solve the assignments problems by in the next week, in the coming week. We'll solve for both week 1 and week 2. And this week we'll just solve some sample problems related to this week's content. And in the meanwhile, you can ask questions in the chat or you can raise your hand and I'll ask you to speak if you want to ask questions in the during the presentation. And otherwise, we'll have a dedicated question answer time at the end of the presentation. Okay, so in the second week, the topics that were taught was the first was the continuation of the device physics. The second was application and analysis of switches, which included Snubber circuits, gate drivers, and a generic converter. And then the course moved on to single phase converters, basically AC to DC rectifiers, uncontrolled, and we've started with controlled rectifiers as well. So in terms of design, device physics, I'll again reiterate the general concepts, the basic principles that I had mentioned last time also, because irrespective of the device, these principles will help you in understanding the basic properties of all these devices. So the basic concept here is that we are using semiconductor devices. So they have uh, special materials that we are using, and in the semiconductor, uh, the substrate is doped with either p-type impurities or n-type impurities. So p-type means the number of electrons is less than the basic substrate. So the number of free electrons. So it will have an opportunity uh, to hold another electron. So it will have a hole instead, and that hole we can consider as a uh, positive charge. So that is why that substance with a p-type impurity is called a p-doped portion of the substrate. Similarly, we can have an n-type doping where we have more number of electrons than the basic substrate. So this p-n junction that we are using is common in almost all the devices, starting from the diode up to all the devices that we've studied in this session as well. So the amount of doping that we do, that means the concentration of the impurities, it has some relation on the breakdown as well as the resistance of the device. If we reduce the doping level, the concentration of the impurities is less, then these extra charges will be less. So we can have the higher breakdown of the device, but it comes at a cost. This higher breakdown comes at a cost of higher resistance because we have less number of charges. So then we will have more resistance to the current, more because we don't have enough charges uh, to move forward the current. But now we can have two type of devices. The first is called a majority carrier device. For example, in N-type material, the electrons will be majority carriers and holes will be minority carriers. Vice versa, in a p-type device, p-type substrate, the holes will be the majority carriers and the electrons will be the minority carriers. So there are devices which in which conduction happens mostly via majority carrier devices, majority carrier charges. And these are called majority carrier devices like MOSFET, Schottky diodes. In this case, just like we mentioned, low doping will increase the breakdown as well as the resistivity. So if we have a higher voltage device, that means the doping level is low, the resistance will be high in majority carrier devices. But in minority carrier devices like diode, SCR, BJT, IGBTs, they have a phenomenon which is called conductivity modulation. In conductivity modulation, what happens is that minority carriers are injected into this lightly doped region because we are using light doping to increase the breakdown level or increase the device rating. But in minority carrier devices, these minority carriers are injected into the lightly doped region, and therefore the amount of charge in this lightly doped region increases, so which reduces the resistance. So basically, in minority carrier devices, we can have the advantage of high breakdown level, that means high rating of devices, together with low resistance. But this low resistance again comes at a cost. And this cost is that when we want to turn on or turn off this device, this minority carrier device, we have to inject this minority charge and then remove this minority charge. And this injection and removal, sometimes injection or sometimes removal, it takes time. And that time increases the switching time of the device. So it takes more time to turn on the device or turn off the device. And that means the switching losses in the device are more. Okay, so for majority carrier devices, because we don't have this conductivity modulation, we don't have any injections, or we don't need to remove any minority charge, the switching speed is high. But for high voltage devices, the resistance will be higher. So conduction loss will be high, but switching loss will be less. Vice versa for minority carrier devices. The conduction losses will be less because of conductivity modulation, but the switching losses will be high because to remove this minority charge, it takes more time. So this is just a summary of the basic device physics and the characteristics of voltage ratings and conduction loss, switching loss. So, and these are the main ratings that are of importance to us. So now we'll just move on from the device physics and we'll come to application and analysis of switches. So first we'll talk about an ideal switch, and this we mentioned in the last week also, but now we'll just go into more details in what is an ideal switch and how does the practical switch differ from an ideal switch. So as it's mentioned, the first property of an ideal switch is that when the switch is on, it offers zero resistance or uh, zero forward drop. So you can see on this right side of the switch, when the switch is on, so it is closed. In that case, we are saying that V on is zero. V on is zero means that there is no resistance because a current I is flowing through the device. But since V on is zero, then that means there is no resistance and there is no forward drop. So that means there is no conduction loss in the device. So a zero on state resistance or a zero forward drop means that there should be no conduction loss in the device. That is what an ideal device should have. But of course, as you know, for a diode, we have a forward voltage drop. Similarly, with all thyristors, there's a forward voltage drop. And for MOSFETs, there's a we can model a resistance in RDS, the drain source resistance. So all practical devices have a resistance or a forward voltage drop, which leads to a conduction loss in that device. So when that device is on, there will be some loss. There will be a continuous loss happening due to that resistance or due to that forward voltage drop. And that power loss will be given by either if we can model that forward voltage drop using a resistance in R, then that power loss will be given by I square R. If we can model that drop using a voltage drop, like a VF zero point 0.7 volt or 1 volt drop, then the power loss will be given by VF times the current. So zero point 0.7 or 1 volt into whatever current is flowing. That will give us the conduction loss. The second property of an ideal switch is infinite off-state resistance or zero reverse leakage current. So what that means is when the switch is off, then there should be no current passing through this device. So that will lead to a zero current, and that we can understand if the resistance is infinite, then we there will not be any current passing through the device. And for the for most of the devices, this condition is actually followed quite well. So we don't have very large reverse leakage currents uh, during off time in practical devices. So if there is a current, it is in microamperes or even less than that, nano amperes. So this condition is relatively followed in practical devices. So we don't really worry about the reverse leakage current during off time for most of the practical devices. So the third property of an ideal switch that we want is to have infinite bipolar voltage blocking and bidirectional current carrying capacity. Okay, so there are a number of things happening in this property. So first is infinite voltage blocking and current carrying. So in all practical devices, there will be a limit to how much voltage level it can block. And that limit is actually called the rating of the device. So for example, we can have a 100-volt diode. So that means it will block up to 100 volts, but if you uh, apply more than 100 volts to that diode, it will break down. Similarly, so this is the rating of the device. And as we mentioned earlier, that this rating is dependent on the structure, the doping levels, how much substrate is there, and all these determine the voltage rating. So ideally, we would want to have an infinite voltage blocking capability. That means however much voltage we apply on the device, it should block that voltage. Similarly, however much current we pass through that device, it should allow it to pass through. There should not be any breakdown or any heating up or any device damage. But practically, that is not the case. We have some voltage limits as well as we have some current limits. So in most devices, the voltage limit is based on the breakdown level, and the current limit is based on the heating. Because when we increase the current, the switching as well as the conduction losses will increase. So that will create heat in the device. And if that heat goes above the device rating temperature, like 150 degrees or 175 degrees, then that device will basically get damaged. So practically, we don't have infinite voltage blocking and current carrying capacities. So another point that is mentioned here is infinite bipolar and bidirectional current carrying capacity. So that means we want a four quadrant device. So an ideal device should be a four quadrant device. That means it will block positive voltage as well as negative voltage. So that is bipolar voltage blocking. And it will carry positive current as well as negative current. So that is bidirectional current carrying capacity. But as we've seen last time also, so uh, all devices are not four quadrants. Some devices are one quadrant, some are two, and some are four quadrant. But most of the devices are either one or two quadrant. Sorry. So the diode is a one quadrant device. It will carry positive current and it will block negative voltage. And SCR is a two quadrant device. It will block positive as well as negative voltage, but carry only positive current. So ideally, we would want to have a four quadrant device, but practically we are limited by whatever we have, and most of them are not four quadrant devices. So another property of a ideal switch is that it should have an instantaneous turn on and turn off. So what does that mean? So when the device is off, it will block some voltage. So there will be some voltage V across that device. And when the device is on, so while the device is off, the current through the device is zero and it has some voltage across it. Now, when the device turns on, then it will have some positive current or some negative current depending on the device. But let's say it has a positive current and the device voltage will be zero. But during this transition from off to on, the voltage has to go from some positive level to zero. The current has to go from zero to that positive level. And during that transition from positive, when the voltage decreases and the current increases, if that transition takes too much time, then there will be some overlap between the positive voltage and positive current. And that overlap will cause switching loss. So in this case, there will be turn on loss. So if the reverse thing was happening, we were going from on to off, then we will have a positive current, and then that positive current will go to zero, and we will have a zero voltage, and that then when the device turns off, it will have some positive voltage. And if that time takes too long, then we will have switching losses in the device. Ideally, we would like to have no switching losses, so the device should turn on or turn off instantaneously. That means this, like I have shown, this is a very high slope, an infinite slope of the current and infinite negative slope of the voltage. But practically, as you can understand, this will not be so. It will take some time for the current to rise, and it will take some time for the voltage to fall. And during that time, we will have some switching losses in the device. So the next property of an ideal switch is that it should be fully controlled. That means we should be able to control when the device turns on and when the device turns off. And as you know, we all devices are not fully controlled. A diode is completely uncontrolled. It depends on the circuit conditions, whether it will turn on and turn off. SCR has, we can turn it on by a gate signal, but it will turn off auto. It will not. The turn off is not in our control. So this is a condition that is not fulfilled practically. And lastly, we want an ideal switch to require zero power to drive the switch. That means we should not. So as you can see, all these properties are related to we want the switch to have no power loss. If there was power loss in the device, that means either conduction loss or switching loss or gate drive loss. We don't want any loss in an ideal device. But practically, we will have conduction loss as well as switching loss, as well as we will require some power to turn on the switch or turn off the switch. So that is called driving the switch. So we will require some power to drive the switch. So that is the difference between an ideal switch and the practical switch. Now, these are just some the ratings of the available devices that we have and some applications. So on in this figure, the x-axis shows the operating frequency, that is the switching frequency. How fast can we turn this device on and off? And the y-axis shows the power level of the device that is available. So thyristors have the highest power level available in the market, but the switching frequencies are limited. So because as you can understand, if the voltage, because these are minority carrier devices, if we increase the voltage rating, that means we are increasing the uh, lightly doped region. So we will be increasing the minority carrier charge. So we will not be able to switch very fast, because if we switch very fast, then there will be a lot of switching losses, and the device will burn basically. So for thyristors, we have very high power levels available, voltage and current ratings available, but the switching frequencies are limited. So, and then from thyristors, we can go to GTO where the power ratings are less, but the switching frequencies that we can use are higher. And but still, for very high switching frequencies in the kilohertz range, we will have to go for IGBTs, where the power level is again reduced, but the switching frequencies are still further increased. And lastly, MOSFETs, because these are majority carrier devices, so we can switch very fast. But because they don't have conductivity modulation, uh, if we go for high voltage ratings, then the conduction losses will be high. So we cannot go for very high power levels, but the switching frequencies we can increase, and we can go in hundreds of kilohertz. So, and BJT is not really used today these days in power levels, in power semiconductors. They are used in signal level processing because the power handling capacity of the BGTs are not high compared to the other available devices. And so these are all still silicon based devices. If you uh, so for because nowadays we have what is called wide bandgap devices, and they are basically composed of silicon carbide and gallium nitride devices, and they will basically come in this range, slightly higher than MOSFET in the voltage ratings and slightly higher than IGBTs in the switching frequency range. So SiC will come here. We can have higher switching frequency than IGBT and higher voltage ratings than MOSFET. And gallium nitride will come uh, to the right of MOSFET. We can go with even higher switching frequencies in the megahertz range, but still the voltage ratings and the power ratings of gallium nitride are limited to slightly less than the MOSFET. So depending on these availability of devices, that is where we will determine what applications can these devices be used in. So for the highest power ratings, where we require in applications where we require the highest power ratings, we will use thyristors. And as we go for less power ratings, so these applications that I've shown, these are from high power ratings to less power ratings. So as we go from high to less power ratings, we will go from thyristors to GTO to IGBT and lastly to MOSFETs. So for HVDC applications and big welding machines, we use thyristors or sometimes GTO. Similarly, for large drives, machine drives, and ships in traction railway applications, we use GTO or very high rating IGBTs. In solar plants where we have to convert from DC to AC or three-phase AC, and in buses where we have electric buses and electric cars. So in these applications, we use IGBTs mainly, or in some cases uh, high rating MOSFETs, SiC MOSFETs. And then if we go further down the power ratings, then in small drives, uh, motor drives or robotics, where we have very small motors to where we require some precise movements in like robotic arms or robotic movements. There we make use of MOSFETs uh, or IGBTs for high power and MOSFETs for low power. And similarly for power supplies like UPS and like power supplies you have in your computers and your laptops, and chargers, adapters. So these are chargers for even uh, mobile phones, laptops, or higher level chargers for EVs or scooters. All these cases, we use MOSFETs with high switching frequency so that we can reduce the size of these uh, components. So this was about the ratings and applications of these devices. Now I'll just briefly talk about snubber circuits. So snubber basically are elements which absorb energy from reactive elements in the circuits. And we use these snubbers to for damping or for controlling the rate of change of voltage and current. Or so is this the case with everyone? Is my voice inaudible? Oh, okay, so I can talk to. Okay, so I think okay, so it might be the case a problem with your internet connection. So, but for other students, my voice is audible. So snubbers are basically used for damping oscillations because in a practical circuit, when you turn on a device, the current will not just go from zero to some positive level. It will go to some overshoot and then will have some slight oscillations. And if we want to reduce these oscillations or damp oscillations or limit the overshoot that can go, we will use some what are called snubber circuits. And so the basic two types of snubbers we have. One is for voltage to control the rate of change of voltage or limit the voltage overshoot, or we can have a current snubber for limiting the current rise or the peak current. And for voltage control, we will use a capacitor in parallel to whatever device or component we have. And for current control, we will use an inductor in series with uh, the device or the element that we have. And these two equations are very important, not only in electrical engineering, but especially in power electronics. These will be the foundation of all the analysis and even your intuitive understanding. These will be the equations that we'll use. So for the capacitor, the derivative of the voltage across the capacitor times the capacitance will be the current through that capacitor. So what does this equation basically mean? It means that uh, you cannot have sudden changes in the voltage of the capacitor across a capacitor. Because if you have a sudden change, that means the derivative of that voltage. Let's say you have 10 volts across a capacitor, and suddenly, in an instant, it rises to 20 volts. That means the derivative uh, of that sudden change is infinite. That means the current that flows through that capacitor is infinite, which we know is impossible. So basically, this equation tells us that the voltage across a capacitor cannot change suddenly. It will have to change in a gradual manner. Similarly, for an inductor, the current through the inductor cannot change suddenly, because again, the same situation will happen. If the current changes suddenly, then the derivative of that current will be infinite. That means the voltage across that uh, inductor will be infinite, which is impossible. So practically, we cannot have infinite voltages or infinite currents. So that is why we cannot have sudden changes in the inductor current or sudden change in an inductor voltage. And so that is the what we understand from these equations. And depending on the capacitor, if the capacitor value is higher, for the same capacitive current, the dV dt will be less. So you can understand, if I keep IC constant and I increase C, then dV dt will have to decrease in order to keep IC constant. So that means for a higher capacitance value, the change in the capacitance is slower. The change in the capacitor voltage is slower. Similarly, if we have a higher inductance, the change in the inductor current will be slower. So that is why we use capacitors to control the voltage or control the voltage rate of rise or the overshoot. Because by adding a capacitor in parallel to the whatever device we want to control the voltage rise of, then the capacitor will not allow a sudden change in that the voltage across the device. Similarly, the inductor will not allow a sudden change in the current of the device. So that is why we use capacitors and inductors for snubber circuits. And we can have different snubber circuits for different voltage, different devices, but I will not go into those details in this summary. So now I'll talk about gate drive circuits. So if you ever, okay, so the question is how about them absorbing energy. So you're right. I have just shown the capacitor and an inductor here. If we only have capacitors and inductors, then they will not absorb energy. But uh, but I was just trying to convey the basic concept. In an actual circuit, we will have dissipative devices as well, resistors in series with the uh, capacitor or in parallel with the inductor, so that those resistors will basically dissipate or absorb this energy, because what we want is also, because the snubber circuit can also reduce the switching loss. They can take some energy, and that energy will be then dissipated in the additional resistors that we will include. So, so you're right. The capacitors and inductors by themselves, they will not absorb energy. They will only just uh, transfer energy from one place to another. But the dissipation will happen in resistive elements that we will include in the snubber circuits. Okay, now gate drive circuits. I was saying that if you ever have to actually work on a hardware power electronic converter, then you will have to pay very close attention to the gate drive circuits. And so these are very important for actual implementation of the concepts that we study. But why do we need gate drive circuits? The basic concept is that whenever in a power electronic converter, we will have these switches, and most of the times we will have some control switches, and we will need to turn them on and turn them off. And so we will require some control signals which will turn in order to turn these devices on and off. But these control signals are usually at logic level. So what does that mean? That means these are either we develop these control signals using op amps or some signal level BJTs, and the voltage level in this is 0 to 3 volt, 0 to 5 volt. So these voltage levels are not enough to turn on or turn off the devices that we want. For example, for a MOSFET, we require more than 10 or 12 volts to turn on the device. But the control signal from the op amps or even for digital control, we use microcontrollers. The output of these microcontrollers is in this level of 0 to 3 volts, 0 to 5 volts. So these control signals are not enough to to turn on the devices. So not only the voltage level, the current that is required. For example, to turn on an SCR, for a very high voltage rating of SCR, we require the currents in the range of amperes. And these control signals will not have that capability. They cannot provide uh, current in the range of amperes to the switches that we want to turn on. So that is why we require some additional circuitry, which is called a gate drive circuitry, to amplify the voltage and current levels and the power level to drive the switches to turn them on and turn them off. And besides this amplification of the uh, voltages and currents, they also provide protection features and some isolation features. So, for example, we studied snubber devices are also protective devices, so they can limit the DVDT or DIGT or the overshoots. And gate drivers also use some protection elements. So we will not study the protection elements here, but I will briefly talk about the isolation, why we need isolation, and how we can achieve isolation. So just to set the stage for this isolation, so this here I've shown on the figure a basic concept of a gate driver. Suraj, do you have a question? Okay. So the gate driver, it basically has two kinds of inputs. One input is the control signal that I've shown here in the terminals S and N. And this control signal will be basically when we want the device to turn on and when we want it to be turned off. And this control signal will be, as I said, in the signal level range from 0 to 3 volt or 0 to 5 volts. So that is one input to the gate driver. Another input would be the power supply. Because, like I said, we want, let's say, 15 volts. We want to give 15 plus 15 volt to the IGBT to turn on and minus 5 volt to turn off. So that plus 15 and minus 5, that voltage we will supply to the gate driver. So that is the uh, supply voltage to the gate driver. So we are giving two things to the gate driver. One is the control signal, and the second is the supply voltages that we want to be applied to the device. But now here you can see The output of the gate driver is Gn. So G is the gate terminal and N will be the the reference terminal across for which the gate terminal is referenced basically. So for example, the G terminal will have a plus VCC when the device is on, and it will have minus VEE come with respect to this N terminal, the capital N terminal, when the device is off. So this is the output. Now, it is not necessarily the case that the capital N will be the same as the small n, but the VCC and VE voltages should be with respect to this capital N. So that is necessary. So I can go into some details with an example. So for example, this is a power electronic converter. We have a single phase AC supply across P and small n, and this we have given to a full wave diode based rectifier. So it will produce a DC voltage at the output, and then we have an IGBT based half bridge circuit. So if you see the voltage of point P with respect to the small n, it is a sinusoidal voltage. It will go positive and it will go negative. But if we want to turn on or turn off these two IGBTs, we have to provide the gate voltage with respect to their emitter terminals. So that means for the top IGBT, we want to provide a gate voltage G1 with respect to the terminal E1. So it should be 15 volts with respect to E1. Okay. So if the E1 voltage is at 10 volts, let's say, if the potential of E1 is 10 volts, then if we want to turn on the IGBT, the G1 should be 10 volts plus 15 volts. So it should be 25 volts. Similarly, if we want to turn it off and E1 is at 10 volts again, then G1 should be minus 5 volts with respect to E1. So the voltage, the absolute voltage, the potential of G1 will be 5 volts. Okay, so for it, so now in this case, what will be the DC bus voltage? So the DC bus, which is this positive and negative terminal, so you can see it is the collector of the top IGBT and the emitter of the bottom IGBT. So C1, E2. And VC1, E2, if we don't have any capacitor here, it will just be the rectified, full wave rectified version of the AC. Now I want to see what will be the voltage C1 with respect to this ground endpoint. So when the supply voltage is positive, then C1 will be connected to the point P. C1 will be connected to the point P. So the voltage rating of the voltage at the potential at the C1 with respect to point N will be the supply voltage for the positive half cycle of the supply. And when the supply goes negative, then basically what will happen is that the P terminal will be connected to E2 and C1 terminal will be connected to endpoint. So in that case, C1 terminal, the voltage of C1 terminal with respect to the endpoint will be 0. Okay, so the point here is the collector of the positive of the first IGBT, the voltage at that collector point with respect to the ground is not 0. It is varying, and sometimes it is positive, sometimes it is 0. Similarly, you can find out the voltage of this E2 terminal with respect to the ground, and it will be sometimes 0, sometimes it will be negative. So if we want to now drive these two circuits, the G1 and G2 voltages should be with respect to their respective emitters. So for example, in the lower IGBT, so G2 voltage should be with respect to this negative voltage in the negative half cycle. However, what is the case? The logic signals that we will have, they will be with respect to this N terminal. So the logic, the gate driver, that is the control signals that we have, will be with respect to the ground of the supply. So it will be 0, or sometimes it will be 3 volts. But in order to drive the IGBTs, we need this gate driver voltage to be with respect to the emitter, which is not the same as the neutral, the ground of the supply. So that is why we will need the supply. The gate driver should have isolation features. That means the supply, output supply of the gate driver should be with respect to the respective emitters. So for the top IGBT, the gate G1 supply should be with respect to E1, plus 15 with respect to E1, and minus 5 with respect to E1 for turning off. So that is why we not only require we require isolation for the logic signal as well as for the VCC and VE supply. So Asif is asking that logic signal is for diode. No, the diode, there is no logic signal for the diode. The logic signal as well as the power supply both are for the IGBT. The diode is uncontrolled. We will not provide any logic signals. So because these are diodes, these are not SCRs. The logic signals as well as uh, the VCC and VE supply, they are both for the IGBTs. The logic signal, because we want to turn on the IGBT at some point, so we will require, so we will have a control signal which will go from the neutral ground to some 3 volts. But for the gate driving, the voltage should be with respect to E1. So we will basically use an optocoupler or some other kind of isolating element which will basically isolate the control signal from this N point to another point. And we will also require a isolation to produce these VCC and VE voltages, because for each IGBTs, the VCC and VE should be with respect to their respective emitters. So there will be one VCC with respect to E1 and another VCC with respect to E2. And for these, we will use separate small transformers or some other kind of circuit like a bootstrap capacitive based circuit, which will basically produce a VCC voltage with respect to emitter. So that is the basic concept of why we want isolation and how we can use isolation to uh, the different methods that we can have isolation, like optocoupler for signal, the logic grades, control signal, and for using transformers for uh, isolation of supplies. So this was about the gate drivers. Now we can come to single phase converters. And in this week, we basically studied uh, rectification, which is AC to DC conversion in uh, only one in one direction. The power goes from AC to DC only, and that is called rectification. Okay, so someone wants to uh, explain each of the half cycle. Okay, so let me first name these diodes. So let me just name the top left diode I will call D1, and the bottom right diode I will call D2. In the positive half cycle, D1 and D2 will be forward biased. So the terminal C1 will be connected to the point P, and the terminal E2 will be connected to the point N. So if we want to know the voltage of terminal C1 with respect to N for the positive half cycle, since C1 is connected to P, the voltage of C1 will just be the voltage of this uh, P terminal, which is a sinusoidal half cycle. And but in the same duration, the voltage of E2 with respect to N will be zero because E2 is directly connected to N, and I'm ignoring the voltage drops in the diodes. So that is for the positive half cycle. Now for the negative half cycle, uh, these two diodes that I was calling D1 and D2, they will be reverse biased. And the other diodes, so the top right diode and the bottom left diode, these will be forward biased. So the P point will now be connected to E2, and then C1 point will be connected to the N point. So the voltage of C1 with respect to N1 in this half cycle will be zero, and the voltage of E2 in this half cycle will be the supply voltage. So because E2 is connected to P, so since in this half cycle Vp is negative, so VE2 will also be negative. So the whole point of this exercise is basically, Virendra, you have raised your hand. Do you have a question? Yeah, okay, you can leave. Yes, yes. So if you go to the portal, you will have one tab for the recordings. So the presentation as well as the YouTube, this recording will be uploaded on YouTube. Yes, the NPTEL or the Swayam site, you will get the link there. Okay, okay, no problem. Okay, so the whole point of here was to show that the emitters are actually not at the ground level for the entire duration of the working. Hema has her hand raised. Do you have any question? Uh, okay, at the end I will. Uh, so either I will show it at the end or in the next session I will post the links of the YouTube channel. But if you go in the portal where you have all the assignments, so week one, week two, at the bottom you should have some live problem solving session recording or something like that. Okay, then they will have an Excel file where you will find the YouTube link as well as a folder, a Google Drive folder with these presentations. Okay, now coming to the single phase rectifier, gate signals applied synchronously to the power supply. Uh, I don't understand your question. The gate signals are not applied to the power supply. The gate signals will be applied to the gate driver, and the gate driver will have a constant VCC and a constant VE. So that VCC will be positive constant. And based on the control signal, the gate signals that we want, it will use that positive VCC or negative VE to produce the final output gate voltages. Okay, so total harmonic distortion is something that, okay, during positive half cycle, gate signal is high. Okay, so there is some confusion happening because I have not shown the gate signal, what the gate signal actually is. The idea here is that the diode bridge will just create a DC voltage, and then using the half bridge, we can transform that DC voltage to some other voltage. But I have not shown the output of the half bridge. So in during the positive half cycle or the negative half cycle, in each half cycle, this diode bridge will actually be switching many times. It will have a very high switching frequency. So in each half cycle, we will turn it on and off. Uh, so that turning on and off is independent of the supply half cycles. But what I wanted to show here is that the emitters of both these IGBTs are not at the same potential as the power ground. So that is why if we want to turn them on and off, the gate voltage, the gate driver will have require isolating elements. Okay. So if you have any more doubts, then perhaps I can explain in the next session with some more details. But right now we'll have to move on. So THD basically is Suresh has their hand raised. Yes. Good evening. About the gate driver. Yes, yes, please go ahead. Sorry, I did not hear the question. So can you type it in the chat? That way I can read it easily. Okay. Okay, so the total harmonic distortion is basically a measure of uh, the purity of the sine wave. So it is basically defined here. If we have a waveform f, it will have a periodic waveform f. It will have a fundamental component f1, and it will have harmonic components uh, f2, f3, and so on up to some n level. And the THD is basically given by this equation where f is basically the RMS of the kth harmonic. So, what is the significance of this THD? Why are we worried about THD? Why do we want to minimize the THD? Because if you see if the THD is zero, that means all these harmonic elements are zero. So we only have the fundamental. Okay, the certificate of internship that is not up to me. So you can ask the NPTEL organizers. So I am just part of this uh, the problem solving sessions. I am not. I don't have the authority for giving the certificates. So you can email the. So you will be getting some emails regarding this course. You can ask them for your doubts regarding the certificate. So I was saying that THD will basically, if the THD is zero, that means the harmonic elements are zero. And if the THD is high, that means the amplitude or the RMS components of the harmonic components are high. And what is the problem with having a high THD? So you can see here, for example, we have a sinusoidal source, and that source will have some impedance, as well as there will be some transmission line impedance. And then we will have our loads. Suppose now we have a power electronic load which has high THD. So it will have a fundamental component of current and it will have a lot of harmonic currents. So that means the current that is passing through here will have a fundamental component as well as high harmonic components. And at this point of common coupling, where other loads are also connected at this point, the PCC, multiple loads are connected. So because of this uh, IS current, which has high THD, there will be a voltage drop across this impedance LS. And since the IS current has high harmonic components, the voltage drop will have a fundamental drop as well as a harmonic drop. So even though the Vs voltage will can, if it is highly sinusoidal, the voltage at the point of common coupling will be distorted. So it will have, because of these harmonic drops, the voltage will not be sinusoidal at this point of common coupling. And that will create problems for other loads. So some loads, like motor loads, we will require high sinusoidal voltages. If the voltage has distortions, then the motor will not run properly. It will have uh, basically oscillations in the torque. Similarly, it will cause some other problems. So, because of these harmonic currents, the RMS current will be higher. So there will be more losses. So they can also be over voltages uh, due to some resonant effects due to the harmonics. And there will be interference. If the harmonics are at high switching frequencies, then there will be an interference with communication and control signals. So that is why we want to have low THD in our currents and voltages. So I'll briefly talk about a uncontrolled half-wave rectifier with an RL load. So when the Vs voltage is positive, the diode will be forward biased. So basically, it will just turn on, and this Vs voltage will come across. So the Vs voltage will come across the load, which is an RL load. So when the diode is turned on, uh, we will have a differential equation that we need to solve in order to find the current. And that differential equation is given here. Vs is equal to the drop across the resistor, IR drop, and the inductive voltage drop, which will be LdIdt. So, like I've said previously, this LdIdt is very important in our power electronics. And if you put so since for the positive half duration, the diode will be forward bias. The Vs voltage will be the sinusoidal voltage. And if you put the sinusoidal voltage here, then the you can solve this differential equation for the current I, and you will get a current with this blue waveform. But what is interesting here in this case is that the current will have some positive value when the voltage supply voltage becomes zero. But because it is an inductor, even though the diode we see that the diode will be reverse biased, but since the inductor current cannot suddenly go to zero. It has some positive current here. The inductor current cannot suddenly go to zero. So that is why it will not allow the diode to get forward a reverse bias. So it will continue to pass current through the diode and until the inductor current becomes zero. And that is why the load voltage will be the positive voltage and some portion of the negative voltage as well. And but the diode, of course, cannot have negative voltage across it. So that is why the voltage across the inductor will basically flip. So it will go from positive at the start and then it will turn negative, and that negative voltage will basically compensate for the negative voltage of the load, and the voltage across the diode will be zero. So you can basically, if you, I will suggest that if you are interested more in how this exactly is happening, you can simulate this kind of a circuit uh, in either MATLAB or some other LT Spice, some other simulating device, and you will understand exactly what is happening here. But the basic concept is that because of the inductor, the current, it will not allow the current to suddenly go to zero. So that is why the diode will not get a reverse bias. The inductor will basically act as it will provide some voltage, and it will cause the inductor current, it will cause the diode to be forward biased until the inductor current becomes zero. So the switches and unipolar, unidirectional, bidirectional characteristics, I have explained in the previous session. So if you go to that YouTube session, you can you will get some idea of unipolar, unidirectional, and bidirectional characteristics. So just to briefly mention about the full wave rectifier. So in the full case of a full wave rectifier, we will have four diodes, and based on whether uh, the supply is positive half cycle or negative half cycle, different diodes will turn on, and that will lead to a continuous current from the input. And because of the RL load, the current has a different wave shape than the voltage. And if the value of the inductance is high enough, then this current will not go to zero. It will have a positive value. This I current will have a positive value. And because of the diode, this current will be reflected in the source current as somewhat of a square wave. And if the inductance is high enough, we can approximate this source current as a full square wave. And then we can see that the THD of that square wave is very high. It is around 48%. Even though the IEEE standards, they they don't allow more than 5% THD. So that means that uncontrolled full wave rectifier, it has a very bad THD. So we will need to do something to improve this THD, and that you will study in the controlled rectifiers or some other uh, IGBT or MOSFET based uh, DC to AC converters. So now we'll come to the problem solving session. And so some of these questions are quite simple. Uh, Power factor correction, so that is not the topic today. I'm not sure whether that will be taught in the course or not, but that is a different area. So the question is, what is the full form of IGCT? And so I'll just briefly talk about IGCT. So the limits for THD are given by IEEE, which will provide you the standards. And so actually they have very detailed limits for different harmonic levels. So from, let's say, second harmonic to some order of harmonics, they will have one limit. So they will have some percentage. It cannot go beyond that percent, and after that harmonic it will be a less percentage, because the lower order harmonics are more important compared to the higher order harmonics, because the higher order harmonics we can filter out using a small filter, but the lower order harmonics cannot be filtered out so easily. So that is why the lower order harmonic standards will be the limit for that those TSD will be less, and 5% is a very general limit that we want to satisfy. So then IGCT basically stands for an integrated gate commutated thyristor. Yes, the lower order means second, third, and uh, even up to fifth, seventh, tenth harmonic, because higher order harmonic means at the switching frequency level, and the switching frequencies can go up to in hundreds of hertz or kilohertz. So the higher order harmonics are basically in that range, in hundreds of hertz or kilohertz. So an IGCT is basically an improved version of a GTO, and uh, a GTO is basically an improved version of an SCR. And the improvement is basically in terms of the internal structure and the gate drive structure. So it basically leads to a lower on-state loss. The gate inductance is reduced, and there is an integrated gate driver in the packaging of the IGCT itself. So the point basically is that IGCT stands for Integrated Gate Commutated Thyristor. It's a thyristor. Uh, it is one of the thyristors. It is not a transistor, and it is not insulated gate uh, like like we have for IGBT. So it is Integrated Gate Commutated Thyristor. So the answer will be A. Now RC IGCTs. So what are RC IGCTs? So I'll just go to the explanation. So the IGCT. So if you remember, and I said uh, IGCT is an improved version of an SCR, sorry, a GTO, and a GTO is an improved version of uh, an SCR. A thyristor is basically a family of devices which includes SCR, GTO, IGCT. So these are all called thyristors. It is basically a name for uh, a family of devices. And SCR, GTO, thyristor, IGCT, these are part of this family. Another family can be a transistor family, where we have BJT, MOSFET, IGBT. So IGCT basically has two uh, uh, availabilities. We can have one which with reverse blocking or without reverse blocking. The basic SCR has both forward blocking as well as reverse blocking, but the thyristor, the IGCT, it is available in basically two forms. One is without reverse blocking facility, which I've shown on the right. So if you go to the quadrant structure, it has positive voltage blocking, but if it does not have negative voltage blocking, then we call it asymmetrical IGCT. If it has both positive as well as negative voltage blocking, then it is called a symmetric IGCT. And basically, it is the difference between a single quadrant and a double quadrant IGCT. Now, if we have an asymmetrical IGCT which can only block positive voltage, we can add an anti-parallel diode. We can add an anti-parallel diode to this IGCT, and it will allow us to conduct negative current as well. So it will only block positive voltage. It will not block negative voltage, but it will allow current to pass through in the positive direction as well as the negative direction. So an RC IGCT stands for a reverse conducting IGCT. So it is an asymmetrical IGCT with an anti-parallel diode. Okay, that is what is called an RC IGCT. So the answer to this question is the RC IGCT, an asymmetrical IGCT which is fabricated with a reverse conducting diode in the same package. So someone is asking why we go for IGCT rather than SCR. So if you study the first and second weeks, basically the point here is then GTO is an improved version of SCR, and it is improved in the sense that we can turn off the SCR also using a GTO. And an IGCT is now an improved version of a GTO. It has improvements like the on-state conduction loss is less, the gate driver inductance rate, parasitic inductance is less. So it has some improvements over the GTO. And so if we say that what is the difference between IGCT and SCR, IGCT will be an improved version. It will have less on-state loss. It will, and also it will allow turning off the device using a negative gate current. So that is the difference between an IGCT and SCR. So now this is a very important question. So in case of high voltage application, we use which of these devices, whether IGBT or MOSFET. And in case of high frequency application, we prefer IGBT or MOSFET. So here I will wait for your guesses. What do you think should be the answer to this question? Okay, so someone is saying B. So you can type in the chat. So what do you think will be the answer? A, B, C, D? Because the question says that for high voltage application, which device do we use? And for high frequency application, which device do we use? Okay, so most of them have answered correctly. So the difference between an IGBT and a MOSFET. So if you see a MOSFET, so this is a very basic way of looking at a MOSFET. It has an NPN structure and a gate with a oxide layer between the gate. So when we provide a positive voltage to the gate with respect to the source, negative charges will accumulate near the gate. And these negative charges will basically provide a channel from between the two n-type regions. So now we have an n-type region which will have electrons. And because of this positive gate voltage, we will now have electrons which will basically provide a channel between one n-type region and another n-type region. So by providing a positive gate voltage, the MOSFET will turn on. So it will conduct current. And if you see the conducting elements are basically the electrons from the n-type to n-type. So these are majority carriers in the n-type region. So MOSFET is a majority carrier device. So that means, as I mentioned in the general concepts, it will have faster switching, but higher turn-on resistance due to the low doping region. Now an IGBT has another P layer here compared to the MOSFET. It will have an additional P layer, and when we apply a gate voltage, so there will be a channel that will be created. But now what will happen is that we have PN junction here at the top. So if we apply a positive voltage and we have formed the channel, so then from the PN junction, if you go back to the diode, in the diode, what happens is that holes are injected into the N region, and that those holes are basically the current carrying. Uh, that is how the current conduction takes place. So IGBT is therefore a minority carrier device because the conduction happens through holes that are injected into the N layer. So due to this conductivity modulation, because of the injection of these uh, minority carriers, the resistance decreases. However, the switching takes more time because now you have to add these, inject these minority charges and then remove these when you turn off. So because of this case, IGBT has more switching loss, but it has less on resistance. So because of less on resistance, we can go for higher voltage ratings and we will not get very high resistance. So the basic concept here is that MOSFET is a majority carrier device. It will have higher resistance but lower, faster switching. But IGBT is a minority carrier device, so it will have uh, higher voltage rating capabilities because the resistance is less, but the switching takes more time, so the switching losses will be more. Okay, so the answer to this question is D. For high voltage application, we will use IGBT, and for high frequency application, we will use MOSFET. Dharmesh, do you have a question? Anirudh, you have raised your hand. You have a question? Yes. Yes, go ahead. Okay, so if nobody has a question, please you can mute yourself. Minority carriers. No, no. Minority carriers reduce the resistance because of the addition of carriers, uh, charge minority carriers. The resistance is reduced, but the switching time actually increases because it takes time to inject these minority carriers, and when we want to turn off, we will have to remove these minority carriers. So it takes more time. So that leads to uh, higher. The switching time is increased, so that means we cannot go to very high switching frequencies because the switching losses will be higher. So in minority carrier devices, the conduction loss or the on resistance is less, but the switching losses are more. Okay. 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 So before going ahead, we can have a short break now for 5 minutes. So we can uh, then resume at 7:20. Okay. So then we will have to go a bit faster because we still have seven problems remaining. Okay. So we'll come back at 7:20. Okay, we can continue now. Am I audible? Just you can write yes or no in the chat. Okay. Okay, so which of the following characteristics are for an ideal switch? Okay, so this we have studied. What do you think is the answer? Yes, so what we want in an ideal switch is we want no conduction loss. So that means the on-state resistance will be zero, and we want no reverse conduction during the off state. So we want the off state resistance to be infinite. So the answer to this question is zero on state resistance, and the off state resistance should be infinite. So someone was asking before about unipolar, bipolar, unidirectional, and bidirectional switches. So that is basically shown here. The concept is if a device can block only one kind of voltage, whether it blocks positive voltage only or negative voltage only, then it will be a unipolar device. So for example, a diode, it can only block negative voltage. If you put forward voltage, it will conduct. So it is a unipolar device. But an SCR, it can block both positive as well as negative voltage. So it is a bipolar device. Now current is basically the uh, bidirectionality of the device. So if a device passes only positive current or only negative current, so only one direction of current, then we can call it a unidirectional device. For example, a diode, SCR, these are all unidirectional device because they can only allow positive current. But devices like MOSFET, TRIAC, so these allow negative current as well. And so most cases, if you add a anti-parallel diode in parallel with the device, then you can make it a bidirectional device because it allows positive as well as negative current. But bipolar device, that is a so you cannot easily make a bipolar device. So you will have to attach two devices in series to make a bipolar device. Okay, so for regenerative braking, the device which is used, and the options are diode, triac, GTO, or diode and triac both. Sorry, triac and G2 are both. So what do you think is the answer? Okay, GTO. Someone is saying GTO. Okay, what is regenerative braking? So motors that we use are basically every motor can be used as a generator, and every generator can be used as a motor. So they have a motoring mode as well as a generator mode. Motoring mode means that the power flows from the supply to the motor. So if you see here, I have shown a supply, then there is a power electronic converter which will change the voltage, the frequency, or some the voltage level or the frequency level, and then we have a motor. So if the power flow is from the supply to the motor, that means electrical power to the mechanical power, then it is a motoring mode. A generator mode will be the other way around, where we have this power flow from the motor to the supply. That means the mechanical energy to electrical energy. And during braking, so you can understand motoring mode if we want to increase the speed or we are running at a constant speed, that mean then we need to supply energy power from supply to the motor. But during braking, it is possible to instead of just because the motor is already running, already rotating, and we need to stop it from rotating. So it has kinetic energy, and we need to just remove that kinetic energy. So one option is to just dissipate it in the motor as heat. Another option is to just give that energy back to the supply, and that is called regenerative braking. And regenerative braking will happen if the power electronic converter is such that it will allow bidirectional power flow. So it should allow power flow from the supply to the motor as well as from the motor to the supply. Okay, so the power electronic converter should have certain features that should allow for regenerative braking. So now coming to the three options that we were given, the diode, the triac, and the GTO. So if you see, the diode will block one voltage, negative voltage, and allow current in the positive direction. So it is a one quadrant device. The GTO, on the other hand, it will, in, in addition to negative voltage blocking and positive current, it will also block positive voltages. So it is a two quadrant device. So if you see the VI, voltage into I, it will have so voltage into current is the power. So if the power for the GTO can be, it can change the sign. So it can be positive as well as negative. For the diode, it will only be negative. Okay, so it cannot go positive. The power, if we say V into I is the power, then for the diode, it will only be, the power will only be in one direction. But for the GTO, the power can be in positive direction as well as negative direction. And similarly for the triac, because the triac is it will allow current in positive direction as well as negative direction, and it will block both positive as well as negative voltages. So it is a four quadrant device. So it will basically allow all positive as well as negative power. So you can see here basically GTU and triac will allow the bidirectional power flow, but the diode will not allow bidirectional power flow. So the answer to this problem is triac and GTO both can be used for regenerative braking. But in general, we don't usually use uh, bidirectional power capabilities for bipolar devices. Mostly, we reserve this regenerative name for uh, bidirectional current flow. Blocking of voltage means basically that, let's say if we have a GTO and if we apply a positive voltage, it will not turn on unless we give a gate current. So that means it is blocking positive voltage. And also, if we apply a negative voltage, because it is a GTO, it has diode characteristics. So it will just never allow current to flow in the negative direction. So it will block both positive voltage and negative voltage. Okay. So it can turn on the positive voltage. It is controllable blocking. But nonetheless, we can say it is blocking. Yes, the GTO does not allow current in both directions, but it is possible that the voltage, because of the two quadrant operation, the power flow can go negative in some cases. So if the voltage was initially positive, then we can. So I understand what you're trying to say. I was going to mention that in general we reserve this term bidirectional power flow for devices which can have negative current as well, positive and negative current. But the course instructor, if you see, he has basically put GTO and SCR both in the regenerative device category. So based on that, uh, I can say that because they have positive as well as negative voltage blocking capability, in that sense, we can say that they can allow both positive as well as negative power. Okay. So the next question is how to turn off the GTO. And the options are by applying a negative current, by having an anti-parallel diode, by having a freewheeling diode, or none of these. Okay, so a GTO is an improved version of an SCR. And I've shown here the structure of the GTO and SCR. So SCR is on the left, and uh, both of them, SCR and GTO, both can be turned on using a positive gate current. And that we can understand. But for the SCR, if we apply a negative gate current, the SCR will not be turned off because the PN junction that is here between gate and cathode, by applying a negative gate current, uh, this PN junction, only the PN junction, that area which is close to the gate, will be reverse biased. But the rest of the PN junction, which is away from the gate area, it will not be reverse biased using the gate negative gate current. So that is why the SCR is uncontrolled turn off. We cannot turn it off using a negative gate current. But in a GTO, because of the structure of the GTO, because the gate is what is called interdigitated, so it is divided in the cathode region. Because of this structure, if we apply a negative gate current, the entire PN junction between the gate and cathode region will be reverse biased. So the GTO will be turned off by applying a negative gate current. So the answer is, by applying a high negative gate current, the GTO will turn off. So the next question is, the switching times of a MOSFET essentially depends on which factors? The frequency of the supply system, the charging discharging rate of parasitic capacitors, the charging discharging of parasitic inductors, or the voltage current rating of the system. So you can give you what you think is the answer. Okay, so someone had said that it's the frequency of the supply system, but as we will see, the frequency of supply system is not uh, important here. So the MOSFET, we can model it using three capacitances. One capacitance between drain and gate. So yeah, these are called parasitic capacitances. So between every two terminal, you will have some parasitic capacitance. So like even between two of my hands, there will be some parasitic capacitance. But because this capacitance is so low, it will not show any features of the capacitance. But for the uh, actual devices, semiconductor devices, they will have higher capacitance. The parasitic capacitance means that it is capacitance that is not intentionally put, but it is due to the uh, just the accumulation of charges, the distance between the terminals. There will be some capacitances. These are called parasitic capacitances. And so there will be some parasitic capacitance between the drain and gate terminal, the gate and source terminal, and drain and source terminal. So these are conveniently named as CGD, CGS, and DS, depending on where they are located. So we know that we can turn on the MOSFET by providing a gate voltage with respect to a source. So once we have a gate voltage with respect to a source, the device current will flow. And that current is dependent on the gate voltage. So the drain current is a function of the gate source voltage. Now the rate at which this gate voltage uh, is charged depends on this CGS capacitance value. If this capacitance is high, then it will take more time to charge CGS, the gate voltage. And similarly, if the gate CGS capacitance is less, then we can charge uh, the the gate terminal quickly. So then if we can charge it quickly or slower, then the switch will turn on quickly or slower. So basically the point here is that CGS will determine how fast the device will turn on. And once the device turns on, first it will be blocking some voltage. So the CDS and CGD capacitances, it will have that voltage across them. And once it will turn on, that voltage has to drop to zero or close to zero. That means these capacitances have to discharge. So depending on the value of these capacitances, it will take some time to discharge these capacitances. So basically the point here is that the value of these capacitances will determine how fast the MOSFET will turn on or turn off. So it is not dependent on the supply frequency or the voltage and so it is somehow determined on the voltage and current rating, but mainly it is dependent on these capacitances. And these capacitances are given in the data sheet, and these are given in the data sheet as CISS, COSS, and CRSS, which are the combination of these capacitances. And uh, you can see their values. They are what is called non-linear capacitances. They don't have a constant value. Their value changes depending on the voltage VTS. So anyway, that is going into more details, but the point here is the charging and discharging rate of the parasitic capacitance. That is what determines the switching times of the MOSFETs. Now coming to the next question, which of the following relation is true? So this is a relation between form factor and ripple factor. So I will not ask you to guess it because you have to do some calculations. So basically the form factor is defined as the RMS value of a waveform divided by the average value of that waveform. So it basically, you can understand if you have a DC waveform, then the RMS and average will be equal and the form factor will be 1. And if we have a purely AC waveform, then the average value will be 0 and the form factor will be infinite. And if we now have a waveform which has some DC as well as some AC, that means it will have a varying uh, waveform, but it is not necessarily a zero average waveform. Then it will have a form factor between 0 and 1. Sorry, 1 and infinite. Ripple factor is uh, given by this equation, which is a square root of RMS of the waveform minus the square of average divided by the average. And it basically tells us how much the ripple is in a waveform. And if I take the denominator inside the square root, I can basically say that the ripple factor is equal to the square root of form factor square minus 1. So now, if I go to the question, if I see the options are, yeah, either the form factor is 1 or the form factor is square root of 5. So if I put a form factor 1 here, then I will get a ripple factor of 0. Okay, I mentioned that form factor 1 means it is a DC waveform. So if it is a DC waveform, then the ripple factor will be 0. There will be no ripple. Now, if the form factor is square root of 5, then if you see that this term will basically become, this will be a 5 root of 5 square, which is 5 minus 1, which is 4, and the square root of 4 is 2, and I'm taking the positive square root of 4. So the ripple factor will be 2. So the answer to this question is A. If the form factor is root of 5, then the ripple factor is 2. So these are just related uh, related terms, and it just tells us different things and how to understand the ripple and AC content in a waveform. So the next question is in an IGBT, the P plus layer is connected to the collector terminal is called as so what is the P layer connected to the collector terminal called? So if you so we briefly talked about it. So it is based on that concept. So you can, what do you think is the answer to this question? Okay, someone is saying A drift layer. Any more guesses? Okay, so again, I'm showing the IGBT structure. So just like a MOSFET, if you apply a positive gate voltage, it will create a channel between the two conducting N regions. But if I see the structure in a different way, then there will be a P layer and positive layer and minus layer. N minus layer means the lightly doped region, and plus layer will be a relatively higher doped region. And similarly, this can be a P or P plus. And the addition of the P layer, it basically injects minority charges into the N layer. So it will inject holes. The P layer is rich in holes. So when we apply a gate voltage and we have a positive voltage across collector and emitter, uh, because of the forward biasing of this PN junction, uh, holes will be injected into the N layer, and those holes will basically carry the device current. So that is why this P layer is called the injection layer, and the N minus region is called the drift region, and this drift region determines the voltage rating because it's the lightly doped region. If we have a more, if you have a greater of the drift region, then the voltage rating will be higher. So since the P region injects minority charges, that is why it is called the injection layer. So the answer to this question is B, injection layer. Okay. So finally, the last question is, in certain applications, it is required that the voltage at some terminal be kept within a certain range. So which device can be used for this application? So the question is asking that we don't want the voltage to go beyond a certain level. We want to limit the voltage to a certain level. Which device will be used for this application, whether it is a PN junction diode, Schottky diode, Zener diode, fast recovery diode. So the question is basically asking about the different kind of diodes that can be used. What do you think is the answer? Is what kind of diode that can be used for this application? Okay, so someone is saying Schottky, someone is saying Zener. So I don't think this was taught in the course lectures, but it is a basic concept that we know that the Zener diodes have this capability of they have a very precise breakdown uh, voltage level, reverse breakdown voltage level, and they can be safely operated in that reverse voltage breakdown level. So it is because of their structure. So they have a heavily doped device, and because of that heavy doping, they have a smaller depletion region. And when a reverse bias voltage is applied, that because they have high doping concentration, so high charges, so with a very small reverse voltage, these charges can get accelerated across the depletion region, and it can lead to a high reverse current. So that is why, so that is called Zener breakdown, and because of that Zener breakdown, they will not allow voltage to go beyond that Zener voltage. And so these devices are used in the reverse region. So they are not primarily used in the forward region, and they are used in the reverse region to limit the voltage to the Zener voltage. Because if the voltage wants to increase beyond this Zener voltage, then it will draw a higher current. And because of that high current, there will be voltage drops in the uh, before the Zener diode circuit, and the voltage will be limited to the Zener voltage. So the reverse voltage remains constant while the reverse current can increase. So that is why for this application where we want to limit voltage to a particular level, we can use the Zener diode connected in a reverse fashion so that it will go into a reverse breakdown region. So the answer is Zener diode. So that was the problems that we had today. So uh, in the next session we will solve the assignment problems for the week 1 and week 2, and if we get time then we'll have some sample problems for the next week as well. And the next week, because of the content that we are covering, next week problems will be mostly numerical problems. So they will mostly be numerical problems. So if you have any more questions regarding this content, you can ask them now. So this lecture is being recorded and it will be uploaded on YouTube, and you can go into the portal. You will have the recording, the the links as well as the this presentation you will be it will be available to you. So any questions? Short application in solar plants. I don't understand the question. What do you mean short application in solar plants? So okay, solar plants. Do you want me to tell you? So basically, there is a number of things that we can do in solar plants where power electronics is important. So the solar plants, if you will know, that they provide DC output, and but we want to connect that solar plant to our grid, which is an AC, which can be a single phase or a three phase AC. So the power electronics is used to basically convert from this DC to three phase AC or single phase AC grid. And so power plants also have a concept called maximum power point tracking. Basically, depending on the solar irradiation, at some voltage, more power can be transferred than other voltages. So these power electronics will also control that voltage, at what voltage the power is being transferred. So we will want the power to be transferred at the maximum power point. So the uh, power electronics is used for that purpose also. Okay. So any other question? Okay, if you don't have any more questions, then we can end the session. So I will be here in about 6 minutes. So if anybody has questions, they can ask. The rest students can leave. Okay. Okay. So welcome to all the students and thank you for joining as well.